Hello, Carol. Yes,
Hello,
we can hear you.
you're all welcome to this webinar. I want all of us to pay attentively and to listen and to watch the videos which could help us in our various workplace and improve our safety standard. We have one of the best service retired fire chief, Jeff Bobonsky, is here to share with us a lot. And we have with us too the president of Encapsulator ACT USA, Mike Reiner. They are all here to give us a lot of experience and understanding about the encapsulator, how we can use it to be safe in our own environment and to be costly effective in everything that we do. So thank you, and I want us to listen attentively so that we can understand our technology. Thank you all.
Thank you, Carol.
Yeah.
Okay, Jeff, we can start, and if we have some question in the chat, I will stop you and we continue with the answer and then move forward. Okay.
Okay. Yep. Very good. I'd first like to welcome everybody for taking the time out of their day to attend the presentation. To give you a little bit of my background, as Carol had mentioned, I was a career firefighter with over 27 years. I'm trained to the level of a hazmat specialist. I'm a paramedic, and anyway, after retiring, I've continued to work in the volunteer fire service, and then began to use some of my experience in the fire service and my training and trying to find solutions for some of the difficult fires that we face as firefighters in today's world. And with some of the problems we have with droughts and water supply. And we'll talk about some of these things as we go through the program. But in my, I guess you can say, quest to find a solution and an answer, I came upon hazard control technologies. And what I want to talk about today is going to be more on the tank farms, how to look at those disasters and prevent them possibly. We'll look at and talk about, fire suppression, our spill control, vapor control, degassing, and the cleaning aspects. So some of the aspects or objectives I want to hopefully discuss is the difference between foam and encapsulator agent. There is a difference, and it's important that we understand the difference so we use the two correctly. Make sure that we're applying them properly and identify the hazards and the emergencies where those encapsulator agents can be very, very effective. So when we start talking about the different types of firefighting agents, as I mentioned early on, water. We all know water, and it is probably the most common. And I often hear in many of our big cities that they have, or we have all the water we need. We have fire hydrants, we don't need foam or we don't need things. But again, I mentioned those drought situations. Water's not free. It costs money to process it and to clean it and make it so it's drinkable. So, I mean, water's not always that free, and it's not always that cheap. So through the years, and especially when we start talking about oil, gas, petroleum products, water's not the solution because those products are going to float on the surface. So firefighting foams were developed. And when we sit there, we talk about those foams, looking back as far as the 1800s, when it was first introduced, it was basically two powders mixed together and entered into a foam generating system to help create the foam, which offered some. And then through the years, we ended up developing those different types of foams that we have now, the protein foams, the aqueous film forming foams, the alcohol resistant. So there's been a lot of advances made, but now we're finding out some of those advances aren't the best. They're not the healthiest. because of the fluorinated ingredients. We're finding out it's bad for the environment. They're bioaccumulative. Once they get into your body, they don't are not easily released. And we've got instances where they can be carcinogenic, cancer causing. So we've got some issues and we're trying to eliminate those fluorinated. And we're looking for a fluorine-free solution. Encapsulator agent has been tested and found to be 100% fluorine-free. So back in '96, Hazard Control Technologies acquired the patent rights for a water additive that was superior in providing cooling abilities. And in the process, we learned that it was very effective on multiple classes of fires. Class A fires, Class B. And when we talk about Class B, I'm not going to just talk about the puddle or the pool type fires, but we're going to talk about the three-dimensional fires, those pressurized flange fires, and things like that. We'll talk about hydrocarbons or petroleum products, as well as alcohols, polar solvents. And we'll discuss the advantages that encapsulators bring in being able to deal with these types of fires. When we talk about the encapsulator agents, we can look at NFPA 18A section 7.7. Under that standard, there is a test, which we call the spherical micelle stability test, but it shows that we're able to encapsulate carbon and hydrocarbons. And once we've encapsulated them, we've made them non-flammable. So we can take a environment where there's been a spill, we can treat that area, and we can make that so that it's no longer a flammable hazard. And we'll see some of that as we go through. But where we differentiate and what this test does is when we sit there and we look at a foams test, the 162 foam test, we're testing a thin wall bubble structure in the presence of high heat under ideal conditions. When we look at a spherical micelle, it doesn't create bubbles. Okay, we changed, and we'll see that in an upcoming slide, but we're changing the makeup of a water droplet. So I want to differentiate the two. One's a bubble, one's a spherical micelle. So what is the basic building block? As I said, it's a spherical micelle that's capable of encapsulating your carbon, your hydrocarbon molecules, your polar solvents, and it can be either a liquid or a vapor. Okay, so again, where foams don't work on vapors, your encapsulator agents can. Okay, and they separate the fuel from the oxygen on a chemical molecular basis. So real quickly, a slide to show you an encapsulator. When we sit there, we look at these spherical micelles being formed, the basic building block, as we said, you've got the polar head, non-polar tail. The polar head loves water, dissolves in water. Non-polar tail, it fears the water, wants nothing to do with it. Once it's mixed using an eductor, or if you're using batch mixing, pouring it into your tank, however it gets into your water stream, it creates these spherical micelles. And as you can see, there's millions of these spherical micelles in the water. So as a water droplet comes out, those molecules nearest to the surface, the tails spin out because, again, they don't want to be by water. And this is how we change the chemical makeup of a water droplet. And by doing so, we change the mechanism of cooling and extinguishing. All of those spherical micelles that are still interior to the water droplet, those spherical micelles interior to the water droplet are the ones that are going to be taking and encapsulating those carbon, hydrocarbon, gases and liquids. And once we've put them into that water droplet, or what we call that chemical cocoon, okay, we keep them. They don't release, and that's what makes those flammable liquid vapors not flammable. I want to show you a quick introduction video to help you understand more about all of the abilities of an encapsulator agent. Again, it's just a real quick introduction. One of the things when I do this video is I would like to point out that if you look to the side, it shows all classes of fires. One of the other things, watch black smoke change colors, quickly turn white. And here in this one, you'll see it for a brief second, there's almost no smoke, but that black smoke quickly turns white, and there's a reason for it. Okay, when we sit there and start looking at your cars now with magnesium, okay, some of your class D metals, you've not only got the fuels as far as class A, but class B. When you look at this video, you'll see that unlike foam, there's no special application technique. Foam has only three application techniques that are recommended, which is rain it in, bank it, or roll it on. Your three-dimensional fires, as we see here, you've got a real quick knockdown and two things are taking place. He's rapidly cooling the metal structure, which is a reignition source, which is that rapid ability to drop those temperatures, and you're encapsulating the fuels. Lithium ion batteries are a new hazard within the fire service. It's growing on a daily basis as far as the applications. While many are wondering what the solution is and how do we deal with those lithium ion batteries, we're finding through multiple tests through third-party agencies, your encapsulator agents are very, very effective. The class D metals, as you can see, there's no sparking, there's no explosions like you would get with plain water. Now, when we look at this energized transformer, you'll notice that there's no arcing or sparking. The energized transformer has completely de-energized. The power's been shut off to it, so it is now a oil, or the transformer oils that are burning. So it's a class B fire in a class C environment. So just so we get that as understanding. So as you can see from that video, we're able to be very, very effective on multiple types of hazards. And I want to kind of discuss a few of those hazards that we continue through the presentation here. When we sit there and start looking at some of our different aspects as far as the petroleum industry, refineries, tank farms, and things like that. But to start with, let's just get a little introduction into encapsulator agent. Class A fires are normal everyday type of fires. When we sit there and we start looking at those, we again are class B fires with two-dimensional, three-dimensional, as well as our lithium ion batteries, and we can be very, very effective. When I was showing the introduction video and I mentioned black smoke turning white, in this overview, if you look under safety, it gives you an idea of what is happening. Okay, encapsulator agents, that white smoke is not steam, it's a warm white mist. And you know, we can show videos of people during training exercises and stuff like that where they mention that that steam is no hotter than a hot shower. So there's no steam that's being created. That's a warm white mist. But the reason that black smoke is turning white is we sit there and we start interfering with that vapor's phase, combustion phase, and we help reduce the smoke and toxicity by 97% in some cases, which means that we're able to also extinguish these fires using much less water. And if you've ever had any experience in dealing with some of these difficult fires where, you know, there's a petroleum product involved, steel structures, and you start to research, you'll find that in many cases, once the fire's out, it could be a matter of hours, you're having a reignition, because that foam blanket breaks down, that metal structure, the metal around the petroleum yet is still hot. As that foam blanket breaks down, if the foam is not reapplied, you have a reignition because of those vapors. So when you start using an encapsulator agent, you're rapidly cooling those metal structures, those reignition sources, and you're helping to make things safer. As I mentioned, unlike your current foams, your encapsulator agents are 100% fluorine free. They're non-corrosive, they're biodegradable, and they help reduce those toxins by 98.6%. So we're greatly improving the environment for the firefighters. And when we sit there and we talk about our everyday firefighting, if there's trapped civilians, if we're not creating steam and we're helping reduce that soot and those toxins, we're making things much safer if there's any trapped civilians as well. So we're giving you with the encapsulator agents, a ability to extinguish fires much quicker, using less time, less water, causing less damage, not only to a facility, but also to the environment. So it makes the way we fight fires on a daily basis in many of these high hazard industries a little safer. So again, we talk about the benefits, that rapid heat reduction, especially on those metal surfaces, use in combination with other agents. I mean, again, when we sit there and we start looking, there are some instances where you may still have to put a foam blanket on a surface to help suppress vapors. But again, we can talk about that as we go through. With your 3D tank fires, I've read in many cases when we sit there and start looking at some of the situations where we deal with fires in industry, especially refineries, petroleum industry, tank farms, etc. A lot of times it's a leaky manifold, a pump, a flange may fail or something like that, causing a three-dimensional fire. And again, if we look at that NFPA foam standard in Annex A11, it even states in there that foam is not suitable to be able to extinguish a three-dimensional fire, which is why we have what started out as a very, very small fire growing into multiple tanks being caught and starting to burn. An encapsulator agent being able to extinguish those manifold fires, those flange fires, pumps, we can prevent and stop those fires from consuming large tank farms, or as we'll see as we move on, being able to probably even prevent a fire or explosions when leaks are detected. So there's many benefits. I want to show a video here. This is doing some training on a tank. This is using naphtha and diesel, a 3% mix. It's 120 gallon. And as you can see, they're sitting there and they're doing a couple of things. They're sitting there and they're spraying over the top. They're trying to cool that tank. And by being able to quickly cool and extinguish, they're able to rapidly extinguish this fire. So what was taking place here is there was a large fire there in São Paulo, Brazil. After the fire had been extinguished, they were testing products to see if they could find something more effective because foam didn't work. And the problem is when we talk again about foam, you have to understand we're talking about a thin wall bubble structure. And in this video, it'll give you an understanding. This is a test that was done with a larger tank in China. They're using a diesel storage with 574 gallons of gas diesel. But it's a good video to show you the differences in the effectiveness of an encapsulator agent versus foams. When we discuss a foam, again, I'm going to go back to that thin wall bubble structure. Thin wall bubble structures can be affected by wind. If it's rainy conditions outside, the rain is going to have an effect on breaking down the bubbles. When we sit there and start looking at this video, you're using an encapsulator agent. I want you to point out a couple things. One, if you look towards the bottom, you'll see that they're spraying the side of the tank with some water, trying to cool that steel. One of the things you need to do when you're fighting a tank fire, especially with foam, because you have to cool the steel. You've got to get that steel cooled down so that that foam blanket can get a footprint and begin to start covering that fire, that oil. Put that layer, that foam blanket on there. And until you can cool and you can start getting that footprint, you're going to be very effective. As you can see, they're using one monitor with a flow rate of 570 gallons per minute. They're using a 3% mix of an encapsulator agent. They're spraying down, and within 58 seconds, okay, they are able to extinguish that fire. It's rather rapidly. 16.5 gallons of F500 concentrate was used on being able to extinguish this fire. As we move forward, okay, we're going to sit there, we're going to get into foam applications. This is an AFFF foam, because again, we're dealing with hydrocarbon. If you'll notice, we're now using 2 monitors. We still have the person trying to cool the sides of the tank, and we now have a couple of hoses. Because that heat on the metal is going to break down those bubbles. It's going to evaporate them away, and it's going to prevent them from being able to start getting that footprint, be able to start making and creating that blanket. So as they're continuing to go, as you can see, they're flowing 2 monitors. Plus, they're trying to cool the sides of the tank. And the other thing I'm going to point out is when you sit there and you start getting into these fires, and as you can see, we're bringing in another monitor, another water supply, trying to cool the tank so the foam can become effective. So now we've got, a couple of monitors on the ground. We've got a couple of monitors adding foam. But again, here's a situation where once that fire's out, even though it's inside the tank, we need to continually do our reapplications of foam, because as that blanket breaks down and until that tank is cooled, there is a source for reignition.
And the other difference, Jeff, that we have to put our view is when you attack the A500 and encapsulate the oil of the petroleum, the remediation is easy, because when you attack with foam and you have petroleum and foam on the top, you have to remediate, take off the foam and take off the ground that you contaminate with the fuel.
Yep. Yes, exactly. And again, because of the fluorinated ingredients in the foam, the environmental hazards, he's talking about many instances where on fires, after the foam has been used, there's millions and millions of dollars in cleanup because of all the foam that's
Jeff,
going
can you
into the
stop
dike
video
there.
here? Yeah, this is Mike Reiner. I want to inject a few things because I'm very familiar with this scenario. When they did the encapsulator agent application. Jeff pointed out that they were spraying the side of the tank to cool. But I want people to understand that that wasn't really necessary with the encapsulator agent. They were doing that because that was what their training told them based on their knowledge of foam. So this is a totally different, a different category of agent, the F500 is. And so that's why you see, okay, they were going, okay, when we use foam, we need to cool the side of the tank so that when we get the blanket built, it can seal off on the side of the tank. And then later, when we see the foam application, we're using twice as much delivery. Instead of 2,000 liters per minute, we're now using 2 at 2,000 liters per minute. So the application rate is 2 times higher. We're using 4,000 liters per minute. And then here at the end, you see we've used 260 gallons of AFFF foam versus 16 gallons of F500 to extinguish the exact same fire. Well, that in itself is a huge difference because you're talking almost 15 times more product. So if you just look at the cost of the products, that's a big difference. But I will also point out that one fire burned for 1 minute, the other one for 7.5 minutes. So during that 6.5 minutes of burning, you burned off enough flammable liquid that you easily pay for the F500, just in cost savings of putting the fire out without, and the saving of the flammable liquid that burns off during that 6 minutes. So huge cost savings of an encapsulator agent application versus foam. And as Jeff pointed out on the last video, that was done in the Parana state in Brazil. They did that after the Santos fire. I don't know if you're familiar with that, but on that fire, one tank caught on fire. And before the incident was over, they burned 4 tanks to the ground, took over 9 days, had a huge environmental mess with all the AFFF foam that went into the marina and everything, resulting in over 27,000 tons of fish kill. So just the environmental cleanup alone for the company, which happens to be Ultra Cargo, was billions of dollars of environmental cleanup. And I think that's what Hernan was trying to mention, is that when you spray your foam down, and you probably have experience with this, you get a lot of overspray, you get foam all over the ground, you have so much more quantity that the environmental cost of the use of an AFFF foam versus an encapsulator it's night and day. And with that, Jeff, thank you for letting me talk.
Oh, no problem. Appreciate it.
Thank you. To be clear, Mike, with my English.
Yeah. It's always good to have additional input. So as Mike was saying, as we go through to the end, it starts talking about the differences in times and the amount of difference. Look at your water that I mentioned earlier. When water starts to be an issue, 535 gallons with 16.5 gallons of concentrate versus 260 gallons of concentrate and 8,395 gallons. So as Mike was saying, the cost savings, not just in the amount of fuel that burned off with the difference in the time, but also in the amount of agent and product agent that you need to be able to use to extinguish these types of fires. So when we sit there and start getting into that 3-dimensional, okay, your distillation columns. I know I've talked with many people in oil and gas industry, get distillation columns. They can sit there and say, oh, hey, it's There's distillation columns, you know, they can be on there for hours trying to extinguish those. Here's a 3-dimensional fire, another really good example of the abilities of an encapsulator agent. If you've got any experience with foam, you'll know that you're not going to be able to put a fire like that out with multiple hand lines, much less just one hand line. We're seeing again the mock-up of a jet engine cowling. One of the things I'm going to point out is the fuel doesn't get shut off. The fire will be out and the fuel is still spraying. So it's not that, you know, hey, they shut the fuel off.
Jeff, can I inject another item here?
Yes.
Can we stop the video for a second?
Yep.
If we go to the NFPA 11 standard, which is the standard for low, medium, and high expansion foam, and we start to look through that standard, we see a lot of design criteria on how to put floating roof on tanks, flammable liquids in a diked area, non-diked area. One thing you notice though is there's not really any design guidelines for 3-dimensional Class B fires. And I was always curious, well, why is that? You know, we have these distillation columns, you have well blow-offs. You have, in like this case here that we're looking on the screen, we have pressurized flange fires. We have instances when we're refining where we might have a gas leak that causes a vapor cloud that eventually finds a hot spot, and boom, we have a huge explosion that causes lots of damage, injures, or possibly even kills the people at the plant. But as you go through the standard and finally you get down towards the end at the appendix, there's verbiage in the foam standard that says foam is not suitable for a 3-dimensional Class B fire. So what does that mean? What that means is that's why you don't see any design criteria for these last 3 or 4 type of applications that Jeff is showing you, because foam's not suitable. So what that does is that leaves you as the end user, as the pipeline supplier, at your truck terminals, at your refineries, it leaves you kind of on an island, kind of holding the bag. Your options are water, more water, and even more water, which that's where this agent really shines, because we can encapsulate those hydrocarbon molecules inside the spherical micelle, and we can separate the fuel from the oxygen, whether it's in a 2-dimensional plane or whether it's in a 3-dimensional plane. So in these applications like truck terminals, tanker loading places, those are really key applications for an encapsulator agent versus foam. And we saw in the last couple videos how it's effective on a tank fire, which we would consider a 2-dimensional type fire. But yeah, I would recommend, Hernan, that we can send a copy of the NFPA 11. That's the foam standard. That's not our standard, but point out where it shows that foam's not suitable for 3-dimensional Class B fires. Thank you, Jeff.
No problem, Mike. So in the video again, we're sitting there, and as I mentioned briefly in my presentation, when we sit there, we start looking at some of these tank farm fires caused by pressurized valves, or flange fires, manifolds, etc. Where foam can't deal and extinguish those types of fires, we end up, and a great example would be one that happened here in the US Deer Park. It started out as a manifold fire that couldn't be put out by foam, and it ended up burning 11 of 15 storage tanks. And as you can see here, with an encapsulator agent, you're quickly able to extinguish not only those flammable liquid, but also with the gases. Being able to cool that that valve and that piping so that you can safely close those valves and shut off source where the fuel is being sprayed from, and encapsulating it and keeping it safe. So as we sit there and we start to talk now about the encapsulator agent and some of the applications, the techniques we want to talk about when using it, because as I mentioned, when we talk about foam, there's only 3 approved application techniques: the rain it down, bank it in, and roll it on. And from the videos that you saw that we've played up to this point, you haven't seen. I mean, we've made an aggressive attack directly at the fire so that we can encapsulate those vapors, so that we can cool that piping, that metal structure. So we want to go directly after the. So this is basically covers an example of a scenario, a situation that occurred where there was an explosion at a facility. It ruptured or put a hole in a tank using asphalt. It spread along, and as it spread along, it was able to be ignited. But again, if an encapsulator agent had been able to be applied, it would have started to cool, okay, rapidly cool. It would have been able to start encapsulating, keeping those vapors down. This could have been prevented. Okay, now we're ending up with the toxic black smoke, talking about evacuating a community. And then they sit there and they start creating their plan on how they're going to make their attack. And it's a multi-phased attack. The thing is like I say, when we're sitting there and we're looking at the use of an encapsulator agent for 3-dimensional, it's able to cool, it's able to extinguish, and we're able to control those combustible vapors, the flammable vapors. And in doing so, again, we're using much less water because we're offering, as we saw earlier, that 20 times more effective at being able to cool. So we could have actually prevented and stopped a lot of the damage that was done at the facility. And when we sit there, we start thinking about that damage. I mean, as that fire grows and it's having an effect, how many months of downtime is a fire like this going to cause a facility? Not only that, is how much are we looking at as far as endangering life and the health and safety of employees as well as the citizens that live around the facility because of that toxic black smoke. So with those encapsulator agents, you know, spraying the tanks, we can keep the other tanks cool, preventing any other tanks from being part of the fire, being involved. We can sit there and we start mitigating the actual tank that the fire or that the scenario occurred from, possibly even preventing the fire from even occurring. So there's many advantages when we sit there and we start looking at how we can protect facilities with encapsulator agent. This is just a quick example showing some safety measures or systems that could be added and designed into tank farms or facilities to offer and provide some advanced protection. We're looking at, you know, concentrate systems that use possibly water-driven proportioners, our fire protection systems. We have rings that go around the tank to protect the tanks, to keep that steel cool in the event that there was a fire. If that flange, the manifold, a pump or something were to fail and catch on fire, rather than losing an entire you know, tank farm or multiple tanks within the tank farm, here we have systems that could be put in place to prevent that from even being part of a problem. And this is just an example. You know, the rings around the tank spraying F500 encapsulator agent, providing that superior cooling capabilities. So when we sit there and we start looking, you know, great example of a storm where lightning strike. I know I've seen and read many scenarios or many case histories where lightning has been a cause of many of these tank farm fires. Once the heat detectors detect that the heat's going off, the system is set off. You're using your encapsulator agent to cool the tanks, not only the tank that is affected, but also the tanks that are adjacent to it, to hopefully prevent any heat from being able to cause the other tanks to fail. This is showing just a real quick example of how an encapsulator agent can help cool and prevent these other fires that may be adjacent to a affected one from being able to stop it from being involved in the scenario. So they're sitting there and they're using the agent and working to extinguish the fire and suppress vapors and fumes much more effectively. Again, causing less environmental issues. I've seen in multiple instances, and Mike has even mentioned it, when we're using scenes like this where there's tank farms or fires, you have millions and millions of gallons of water and concentrate in some of the cases that are being used, and we have to do something with it as far as cleaning it up. And I know, and there's been in many cases, one of the most recent ones that happened here in the US, there was so much water that was used, the containment dike around the farm ended up failing, and all of that water, oil, gas that was within the confined area was released into the waterways, and again, causing millions and millions of dollars in environmental damage and cleanup.
Jeff,
Yes.
before we continue in this application, I want to invite Carol if he can share with us the case history, I believe the last year, that there were a big fire in Nigeria, and they finally use this technology. Carol, are you listening? Are you there?
Yeah, I'm here.
Carol, can you share with us this case history, please?
Okay, there was a place where we have a spill in one of the tank farms, and they have a spill, and initially when the spill started, they were having a fire, but luckily they tried to use foam to try to see how they can blanket, but unluckily for them, they used about four drum of AFFF foam, which they were fighting with the fire, and it was not happening, and the spill was still going. What they now did, they used the F500 to I did neutralize the spill where the spill was happening, and at the same time to put off the fire. And everything was put under control in less than 4 hours. They were able to put everything under control, and the fire was off.
Thank you, Carol.
Yes.
Okay.
Okay.
Yeah, thanks, Carol. Like I say, and you know what? It's always good to get some case histories and some actual examples. We're
Yeah, I think,
experienced with it.
sorry, Jeff, I think one more, I think we'll have another case study again in one of the NMPC facility, but there was no fire. There was a spill in around the tank and they used it. And luckily for them, they were able to put everything under control. Some of the MPSC staff, I don't know if anybody from the Port Harcourt houses is yet, they can give you a first-hand situation on that case study too. Yeah.
Okay.
Yes, another other case history was the last weekend that we have, Jeff, a tank fire in Paraguay, here in South America, and they have only 20 pails of A500, and when the fire is so big, they can use these 20 pail and they can download the fire, and then when they cool the tank, they start to apply a foam because they don't have more A500 to finish, to extinguish the fire. But before they apply the A500, they can be so close of the fire. We have,
When you mean be so close, do you mean they can get closer because of the cooling, or it established terrific knockdown of the fire and reduction of the heat that it made it simpler for the foam?
yes, they reduction the heat, Mike.
Okay.
Yes, I have.
And oftentimes we forget that heat, and we sometimes stay so focused on separate the fuel from the oxygen that we forget heat is one of those legs of the fire tetrahedron. If you get rid of the heat, you get rid of the fire.
Yes. Yes, yes. Okay, thank you, Jeff. Sorry for our inputs.
Oh, no. It's always good to get some additional viewpoints. I appreciate it. But like I say, a lot of good information. So the next part, moving on with the presentation, so we'll start talking about that and what was just mentioned with the spill at the refinery or at the facility. We'll talk about that spill control, and we'll talk about not only the flammable and combustible liquids, but corrosive liquids. So we want to talk about some of the proven effectiveness of being able to neutralize compared to foam. Again, foam is going to put a blanket on it. It's not going to do anything to reduce or eliminate the hazard. You're going to have to, once you put the foam on there, call in a environmental cleanup company, or you're going to have to call somebody in to come clean it up and make that scene safe, because the hazard is still there, been covered over. You haven't done anything, so you haven't eliminated, or you haven't gotten rid of the hazard. So we'll look at that and how an encapsulator agent is able to encapsulate those. Okay, we look at the economy as far as generating very little runoff. We're going to encapsulate it. We'll use our monitors, our LEL meters, make sure that our LELs are reading 0. Once we've allowed that to happen, we can allow Mother Nature to evaporate that hazard away, that spill away. And during that evaporation process, we can continue to do air monitoring, and we'll never get into a flammable scenario again. With our foams, we're going to have to continually reapply. Again, that blanket's going to break down, so you need to continually reapply it until the cleanup operations are ready to take place, because as that blanket breaks down, that hazard is going to come back. And if it finds an ignition source, okay, or somebody walks through it, or somebody drives through it, they've disturbed that blanket and they've made that scene more hazardous than before. So we need to look at that cleanup cost. because again, the foams with the fluorinated ingredients, they're an environmental hazard as well as a health hazard. They can get into the drinking water. I can show case histories and scenarios where areas for fishing, where cattle are raised, milk cows and things like that. The milk has to be destroyed because of the drinking water for these cows has been contaminated with the PFOS or the fluorinated ingredients. And as the cows are drinking the water, it's contaminating their bodies, it's getting into the milk. So now these dairy farms cannot sell the milk. So the effects of allowing those foams to penetrate and saturate into the ground and not being cleaned up can be costly well into the future. So that's where we start talking about the hefty cost of cleanup versus allowing that hazard to be mitigated by using an encapsulator agent, very little water, no reapplication, and allow it to evaporate away. Much more effective and efficient. So when we sit there and we start talking about the water, again, when we look at your encapsulator agents, if you know what you have available is salt water, it works well with salt water. I can speak from experience, especially when they start talking about the ships. I was called upon to emergency scene in Vietnam where a tanker ship had sprung a leak and it had flooded the engine room and basically the rear of the ship with thousands of liters of gasoline. The main amount of the gasoline had been pumped off, but yet the bilge area was still heavily contaminated with gasoline. And the shipping company and the insurance company and even the government thought it was going to take months to clean this ship and cost millions of dollars to get this ship cleaned up and be able to be operational again. Using salt water and a 3% mix of F500, once I was on scene, we were able to actually get that ship cleaned to a 0 LEL within 4 days of application. On the overall, I think, and when I sit there and I say 4 days, I'm not saying that it was many hours of pumping solution in. There really wasn't, as far as actual times of pumping. The 3% mix of F500 to encapsulate those fuels, we probably only had maybe about 30 hours of actual application time. The rest of it was moving hoses around, pumping out the encapsulated fuels, and mitigating some of the stuff as we were doing it. So it was very, very effective. We had that ship, as I said, cleaned up from thousands of gallons of liters of gasoline still in the bilge area, and it was clean and ready to be repaired. So continuing on, we look at the regulations for the water and fuel, as I mentioned, with the spill before, allowing it just to evaporate away. I know here in America, the United States, many states allow for that to take place when we sit there and we have auto accidents or we have spills on the ground, where we can encapsulate those, monitor, make sure it's reading 0, and we allow it to evaporate away. So when we look at the difference between the foam again, the foam, if you're using absorbent materials, your absorbent materials, again, while they may reduce some of the vapors, they're not eliminating the vapors. If you were to use a absorbent material and it were to pass a torch over it, you're still going to have flames and fire. There's still the problems of disposing of those absorbent materials. And in many cases, when you dispose of those into a trash, again, you've done nothing to help the environment, because as the oil in those absorbent materials gets squeezed because additional trash gets put down on top of it, that pressure is going to push or squeeze and cause that fuel to come out, and again, contaminate the soil around and possibly even causing issues with drinking water. Carol can probably speak about this a little bit, because some fires that were there in Nigeria. I believe this is a tank truck, isn't it, Carol?
I'm here, Jeff.
Yeah, is this this was one of the fires, the videos that you shared. Is this a tank truck fire that
Yeah, this is a tank truck. This is a fire in Kogi State.
okay. And then the after they used the F500.
They use the F500, yeah.
Okay. And they were quickly able. Now, one of the things that I want to point out, again, speaking from experience with a tank truck fire, I've in my career experienced just such a thing. And I actually, in the process, called for an airport crash fire rescue truck, which carried 3,000 gallons of water plus foam. I, again, was in charge of a hazmat response team, which covered 17 communities, which is in the area just south of Detroit, Michigan. And that tank truck fire actually burned itself out. We were not able to extinguish it. It was a 3-dimensional fire, which, again, we've mentioned multiple times, foam is not suitable for being able to extinguish. When the fire was extinguished, was finally, I guess you could say, burned itself out, on a major highway, there was so much heat, it scalded the concrete down 4 inches deep. Couldn't open it up to traffic. So they actually ended up having to tear up 6 lanes of a highway and replace the concrete before they could allow traffic to be reuse that highway. Millions and millions and millions of dollars in infrastructure damage. But yet here we see you've got this major fire going, F500 has been used, and as you can see, it doesn't look like that concrete underneath that tank where this gentleman's walking was affected very much by the heat that fire generated, because of the ability of your encapsulator agent, your F500, to rapidly and extinguish these fires. And here's another example. When we sit there and we start looking at that spill control, okay, that flammable hazard. Here we're in this example showing, again, the difference between a foam and an encapsulator agent. He sprayed half of it down. The half that he has treated is not burning. There's no bubbles, okay? It's that white milky discoloration, which is how you can tell the product is in the water stream, because we do give it that milky white discoloration. Again, no bubbles. He's gone. He's extinguished the rest of the fire. He's now adding a little extra just to make certain that he's encapsulated it. But is another visual to allow, again, when we talked about that breaking the foam blanket, walking through it. Watch, he slides his foot. He's encapsulated that fuel. He's made that non-flammable. Okay, that can now just evaporate safely away. No special cleanup needs to take place. No fluorinated ingredients. There's no environmental hazards there. So if there's a spill, a ground spill, yeah, it can be treated with an encapsulator agent and help to remediate those spills as instead of having to dig them up if they're of a small size in nature. So next thing we want to talk about in the applications is vapor control. Okay, we've seen and we understand how we're able to work on liquids, but You know, we've also got those flammable gases and combustible gases and things like that. One of the things that we like to talk about is our vapor explosion systems, being able to mitigate those and prevent those from happening. So again, when we start looking at those refineries, we start looking at some of the different areas where leaks can occur. If we've got monitoring taking place, and that monitor is hooked up into a fire suppression system, okay, when those vapors start to rise up before they reach that flammable or that explosive limit, that system could be activated. Your encapsulator agents could be sprayed. They can encapsulate those vapors, and they can prevent a fire or an explosion from ever occurring. Okay, again, when we point that out and we start looking at some of these refinery, some of these explosions that have occurred, just think of how many lives, how much damage to the facility, and how many months of downtime it's caused, and it can be prevented. So when we talk about that VEEP system, the encapsulation, and I mentioned refineries, but you can see, I mean, there's so many. Any place where there could be a possible flammable atmosphere, chemical plants, power plants, all of these other high risk areas. And it shows in here on one of the statistics how the fire departments on average respond to 51,600 annually, where flammable gases have been identified as the source of ignition. Just quickly showing this video. You know, here a person's in an area where it's supposed to be safe to be able to smoke. It wasn't his cigarette that started that. I want to make that clear. If you look at the video, and I'll back it up here a little bit again. If you look at the video, the fire comes from the side. It doesn't start here. Okay, so he's in a safe area, but again, you've got those flammable vapors, okay, which have caused severe injury to employees. As you can see, as he runs off, you have clothing that's on fire, and so on and so forth. So with that monitoring, if LELs had been detected, the VEEP system could have been activated and those fires and explosions could have been prevented. Here's another example showing the violent explosion that takes place. Again, the fire. I mean, the problems and the hazards to your employees as well as the community.
Jeff, can we stop this for a minute?
You can.
You know, everybody knows that what we're looking at here is a disaster. We have major destruction. We certainly have injury, absolutely loss of life. And I don't know if Nigeria is similar to the US, but at this point, we would be responding to this emergency, you know, with fire trucks and utilizing foam to try to extinguish all these fires. And, you know, we know here in the US, the attorneys are going to arrive at the scene before the fire trucks, and they're going to be looking for people. And this is going to end up in huge amounts of litigation. And what Jeff is saying here is with the F500 encapsulator agent, and what the basic building block of that encapsulator agent being the spherical Micelle, all of the things that are needed, the detection equipment exists. We can detect the vapor leak before the explosion. We can send a signal to the fire panel. We can set these things up in zones so that the signal goes to the fire panel that says turn on the fire pump, go through the proportioner, pick up encapsulator agent, sprinkle this atmosphere, encapsulate the vapors, prevent the fire. A second signal then can go to the operator that says, hey, we have a leak in zone 2. Shut down all the valves to zone 2 to isolate zone 2. So this $1 billion of damage and loss of life can now be prevented because of this invention, the spherical micelle, that's the basic building block of the encapsulator agent. So what you're seeing here, witnessing today, is really the opportunity to be able to be proactive to prevent this type of incident, as opposed to just being reactive to go put this fire out after the incident happens. Where I see this system really being effective is where we're loading trucks, tanker things, where we're moving product around, it spills on the ground, vapors are created. You can have an automatic system that will start to dispense an encapsulator agent and encapsulate the vapors while it neutralizes fuel that's on the ground. So, I would encourage, if you want to know more about these systems and how they would operate, these are really custom designed systems for the type of hazard we're trying to protect. But this is a whole new segment in fire protection and safety that Jeff's talking about here in this portion of the presentation.
Yes, thank you, Mike. Yeah, so as he was saying, I mean, this is, again, explosion like this is months possibly of time where you're down. Your facility is going to have to be repaired. What is that doing for your employees as far as income? If the plant's not operational, you've got people that are no longer working. I mean, this is going to cause a hardship not only to the company, but also to your employees. So these are things that we can help to, with the encapsulator systems, prevent as far as the downtime and the damage and the destruction that these violent fires can cause. Let's see. So when we sat there and we talked about that VEEP system, the vapor encapsulation explosion prevention system, again, we started looking at those pumps, those valves, the flanges, and some of the other hazards where we can end up with these fires where they occur. And again, it's not only in that liquid state, it's also vapors. Okay, your natural gas, your LP gas, and things like that. These systems can be activated and they can quickly extinguish the fires. Not only extinguishing, but again, I'm going to get back to that cooling. Okay, that ability to cool the steel, that is that reignition source. Okay, so you're going to be doing multiple things: cooling the steel, encapsulating the fuel. Hopefully, your safeties and your devices that will shut off the gas or the liquid can activate. And again, your explosion and your fire is absolutely eliminated, the hazards. So the benefits are huge. One of the other areas that we'll talk about next is going to be that tank degassing. And I mentioned from my experience, the ship, but here we start getting into the degassing and decontamination and cleaning of above ground or even underground storage tanks.
Jeff, sorry, but before we continue with this application, we have a question about how environmental friendly is the A500? David make this question.
Okay. F500 again, it is environmentally friendly. There's no fluorinated ingredients. It is biodegradable, so it's not going to stay in the environment. When we sit there and we start talking about the encapsulation abilities, when we look at petroleum products, it's actually going to speed up the bioremediation process, the naturally occurring bioremediation process. It's actually going to help those organisms to multiply and help break down those petroleums in the ground so that it can remediate quicker and safer. And again, it's going to bioremediate. It's not going to stay in the environment. It's non-corrosive. So it is much safer than
Yes,
foam.
and we have the EPA and list this product in the EPA, Environmental Agency of USA.
Right. It's also on the US EPA's National Contingency Plan as a surface washing agent. Environmental protection agencies approve the product for use on many pipeline incidents where in one case that I'm very familiar with, it was used by a nature preserve, an area that was protected. And they were very, very adamant that foams and other environmentally hazardous, I guess you could say, additives or water additives or the normal process wasn't used because they didn't want to add any organisms into the environment. And so after we shared with them our test results and things like that, I mean, they approved the use of F500 for helping to mitigate some of these pipeline spills. So as far as the environment, it is very, very environmentally friendly.
Yes, and we will talk about this, about cleaning and remediation in the last application about tandas gassing and this.
Right.
Okay. Thank you, Jeff.
Oh, no, you're welcome. So when we sit there and start getting into the hazards and stuff like that with these above ground or underground storage tanks, being able to clean them, again, we're removing that flammable hazard. We're helping to clean that atmosphere so that people, workers can get inside and start cleaning those tanks, reducing the amount of time that they're down, being able to get in there and clean them quicker, being able to get that tank back operational, or in the event that the tank's going to be removed because it's old and needs to be replaced. Being able to get it to a point where it's safe to clean, fix, or whatever needs to be done in a much safer, faster way. So if you're looking at some of the benefits, you know, as far as the tanks, if you're going to change from, let's say, a petroleum product to another type of product that you're going to store into the tank, you know, you need to be able to go in and clean that tank beforehand. You can speed those up with your inspection and repairs, and as I mentioned, the decommissioning, but that's sludge accumulation. We know that we can have some issues and some problems over the course of time, and that sludge, and if you start getting moisture and water in those tanks, especially when you start dealing with diesels and things like that, some of the bacteria and stuff that can form, that could cause the tank to start to rust or degrade quicker. So you have to be able to get in there and clean that sludge and clean those tanks. And we're seeing a case history comparing the two. But again, we're trying to improve the safety for the employees by making a safer atmosphere, reducing those vapors, make it much safer for people to enter into those, eliminating those gases, not requiring as the ventilation like you might normally get, and the downtime. again, you know, you have those storage tanks and you're cleaning them. If you can change the amount of time from days to clean a storage tank to hours, it would make a huge amount of difference in production, your productivity, and being able to get that tank back operational and back online. But again, we want to key on that safety for the workers. Okay, we want to make that atmosphere within those storage tanks before they enter and start doing any of their work. We want to make those conditions within the tank safer. We want to show in how we can substantially reduce the overall cost in cleaning. That reduction, again, as I mentioned, of the downtime where that tank is offline for any length of time, and the environmental impact. As you've noticed, as we've gone through all of the different points of this presentation, how many times have we mentioned that environmental impact, being able to reduce and minimize it? And then minimizing that hydrogen sulfide, the H2S levels. So this is a example that was shared with us, dealing with the microorganisms and different types of fuels that are able to grow, and the funguses that, in this particular one, they're referring to as the diesel bug. So when they sit there and they start getting into these, we have to get in and clean these tanks because they will cause filters to plug up, blockages that can cause, you know, the tank corrosion if left unchecked, and they can lead to other problems and hazards as well. So they need to get in and do maintenance and cleaning them. So this is a case study where there was a 60,000 US gallons of diesel, and they were working to clean it and mobilized on site. They were going and to work on it. So they first had to bring some trucks in, of course, to empty the tank so that they could begin the process of cleaning it and starting to encapsulate the residual flammable liquids and vapors. They started doing their monitoring, checking for the LEL and the VOCs, volatile organic compounds, and they had all the levels near zero in, as this shows, within 1 hour. They sat there and they start going in and doing their cleaning. Again, while air monitoring is still taking place in their above ground storage tank. The picture showing some of the waste that was removed from the above ground storage tanks, and you know, the water that was, but it's showing the above, the before and after. It's showing the fungi, the contaminated, the soiled, or the, I shouldn't say soil, but all the sludge in the bottom of the tank. And then as you look over to the side, on the other side, you're saying that after they got done with their tank cleaning, it shows how clean the tank is. And again, your readings are zero. So here they took a heavily contaminated tank and they were able to clean it. And then they were able to clean it in a quick, short amount of time. You know, being able to start making or zero LELs within an hour. This is another comparison of tank degassing that was in Brazil, and this is using nitrogen. And with F500, it was a matter of an hour before they had the LELs and the VOCs down to zero. Here we have a 1 million liter. They were using nitrogen. So they sat there and they used the nitrogen application for 4 hours. And this is saying about 4 to 6 hours. After that, they have to sit there and they burned off the nitrogen and the flammable vapors. Okay, once they burn those off, and again, it's showing 4 to 6 hours, they open one door at the base of the tank, monitoring, start doing their air monitoring, checking for explosive atmospheres. If the LELs are low enough, then they can open a second door to allow some additional ventilation, but they need to then allow it 2 more hours to allow that nitrogen, because again, that nitrogen is going to be a atmosphere that's not safe for people to start entering unless they're wearing breathing air systems. So you're looking at hours of being able to ventilate and using compressed air. And this is showing a degassing cost of approximately $3,500. When we go back and look at that F500 tank degassing, again, same tank. They're using a 1.5 inch with a 95 gallon per minute, or was they showing 12 bar, 20 minutes. Okay, so here we went from 4 to 6 hours and then allowing another couple hours for it to ventilate. So we're somewhere between 8 to 10 hours. Okay, 20 minutes. F500 used 3% mix. They sat there and they were able to drop the LELs and the VOC down to 0 in making the entry and start cleaning the tank. So they're showing that the amount of F500 that was used was 60 liters. Degassing cost $1,000. So we're looking at multiple savings here. Now we're looking at the savings of $2,500 just in the cost to clean the tank, but now the hours. How many hours? How many man hours? Okay, you had people on scene for 10, 12 hours on the nitrogen, people on payroll. Here you're sitting there, and on the other one, you're using much faster. You're able to turn that tank over, and you can get that tank back online. You can start using that tank again much quicker. You can start performing the repairs that may need to be done to that tank faster.
Jeff,
Yeah.
let me give you
Yep.
something about the tank disgassing, because I was there in Brazil when we made this test the last year in March, before start the quarantine or all this pandemic.
Right.
In this case, is like Mike said before, that when you understand that this is other technology, different of foam, you can start to understand how work the Micelle, and you can encapsulate vapors, you can encapsulate spills, you can protect your people, and you can protect all the facility. And in this case, in Brazil, this company understand this technology like other technology, and they start to test around all the last year, and they work here, they test here to disgassing this tank, but to make tank disgassing. But last year, they can make tank disgassing and clean the tank only in half an hour. Yes, they spend 30 minutes to disgassing this tank and cleaning this tank. And this is a wonderful example when you understand how work, and this is no another foam product. This is other technology, different, that you can use in different applications, and you can protect your facility before the incident and after, or in the middle of the incident. You can down your hazard of the damage of your facility is wonderful, because more you understand this technology, you can apply in different parts of your facility. Thank you, Jeff.
Oh, no, thank you.
Hernan, this is Mike. I wanted to ask a quick question here. Didn't normally it take about 4 days to degas and to clean these tanks?
Okay, can you repeat, Mike? Sorry.
Okay, my question is, if I understand correctly, it used to take, using the conventional methods, about 4 days to degas and clean the tank to make it ready for a different type of product?
No, in this case, with this tank, the disgassing time to push the vapors with nitrogen, they take almost 6 and 8 hours. Then when they measures the level, when they don't have more vapor, they open the doors and they have to wait 8 hours, and then they can enter in the tank to clean the tank, and maybe they spend 24 hours to clean this tank of 1 million liter of
Okay.
product.
Okay, so
Yes.
8 hours of application of the nitrogen, 8 hours to allow it to dissipate, and then another day for cleaning. So technically almost 2 days to clean.
Yes.
Where here we're talking a half hour to degas, and using the new Thunder system, they clean and degas within like 45 minutes. It takes longer for the inside of the tank to dry now than it does to degas and clean.
Yes, the problem in Brazil, Mike, was that they have a lot of incidents and accidents of the people inside of the tank. And the goal of this kind of company in Brazil is work to clean in the tank without people inside of the tank. And with the new technology of Thunder and A500 in Brazil, they can put A500 in 15 minutes, 10 minutes, sorry. 10 minutes, they wait to that's the solution with the vapors down, and 10 minutes to clean with water. And in 30 minutes, they have all the vapors out, and they clean in this tank without any person inside of the tank.
Yeah, so I'm going to help Hernan with his English. After a series of tests that were run in Brazil with a company called Ageo, we have worked with another company to develop a piece of equipment that we are calling Thunder. And when you put Thunder with F500, which I'm going to call lightning in a bottle, so you put Thunder and lightning together, we are able to degas this 1 million liter tank and clean the tank in under 1 hour. So that is huge from a cost savings point of view. Not only were we able to do that, but without putting people inside the tank. So that is huge from a time savings, just degassing and cleaning your tank. But more importantly, usually you're cleaning a tank to do corrosion inspection and maybe put a different type of product inside the tank. You might be switching from crude oil to diesel or crude oil to gasoline. So you get your tank that much faster, which is a huge cost savings. So if anybody on this call is involved with maintenance of terminals and tank degassing and supply, they should get a hold of us and we can talk in greater detail, because this is a huge development in the world that can save a lot of money. Thank you.
Yes, and then Chef, and in Brazil they make a test to change product diesel and clean with this encapsulator agent. And when they run the test, they don't have to clean a lot. They clean only once, and they can, when they test, they don't have any diesel in the tank, and they can put alcohol inside.
Okay.
Another way, in the normal way, they have to clean 6 times more with the normal product to change diesel by alcohol. Okay, thank you, Jeff.
Oh, no, thank you. That's interesting to know. So you have to clean it multiple times the old way.
Yes.
to get the diesel out, to switch from alcohol to diesel. Interesting. Thank you.
Yes, no problem.
So, you know, again, we start talking about that quick return of the tank to operation. You know, you're looking, as Hernan just mentioned, you know, going from diesel to alcohol, having to clean it multiple times, which again could lead to multiple days that that tank is not operational. We're now using Thunder in an hour. Okay, so basically, you know, you're looking at less than half a day. You're basically can get that tanks empty, cleaned, and back operational. As far as your tanker ships, I talked about that one where I was called in to clean after an incident that took place. Again, the expectations were it was going to take months to possibly a year, and it was done in about 4 days without a lot of expense. So we're looking at that risk, the exposure. We're looking at a higher amount of safety for your employees and your facilities, your labor cost, being able to reduce your labor cost, and that fatigue and injury where, you know, employees can get hurt in doing some of the applications and things that we're looking at. And again, that environmentally friendly. All through the presentation, hopefully we talked and mentioned that it is environmentally friendly, it's safe, not only to the environment, but also to the employees, because it doesn't have the fluorinated ingredients that we see in foams. So when we sit there and start looking at some of the equipment and some of the systems, our loose mobile equipment, our 6-liter and extinguishers, 2.5 gallon extinguishers, our quick attack mobile units that come in various sizes from your 25 up to 100 liter, the portable carts, the yellow carts there, our compressed air systems are in 10, 30, 60 gallons, our mobile response trailers. Again, there's multiple applications, multiple pieces of equipment that we can assist with. And when we started talking about those larger systems to help protect the tank farms or some of the other applications, you know, we have our bladder control systems and water driven and portioners and other pump systems that we can work with. As far as even consulting and training, we offer those services as well with the coal handling, dust hazard analysis, emergency response planning, and then our different combustible dust and bulk storage, coal handling, and emergency response trainings. So before I get into the questions and answer, I just want to kind of wrap this all up, because all through the program, we've sat there and we've talked about the different applications. We've talked about fire. We've talked about spill. We've talked about degassing, tank cleaning. This is one product, okay, that's able to provide all of these different applications, okay? It's not having to buy multiple products, okay? You can purchase one product and you can take care of your lithium ion batteries if you've got electric powered vehicles or electric equipment. You've got for ordinary combustibles, for your polar solvents, for your diesel, for your tank degassing, for your spill control. You're not looking at having to purchase 5 or 6 different products, a different product for each application or each type of incident. It's one product that you can do and have, train your employees how to use it correctly and what application rates, and be able to protect your facilities far better than you currently are able to with the technology and the products that you have with foams, as I said, not able to work on those 3-dimensional fires. Being an environmental hazard, causing contamination to the drinking water, requiring expensive cleanups when you use and you apply them. So with that, I again want to thank you all for being present and having an interest in being part of our presentation today.